So the problem statement here is about the heterogeneous azeotropic distillation. So we are going before we start the simulation, what is meant by this heterogeneous azeotropic distillation and what is the theory behind that is see when our feed mixture consists of an any azeotrope, the one way to separate a mixture containing azeotrope is to add a light entrainer. When we add that light entrainer into the system, that additional azeotrope can be formed that helps in the separation of that azeotrope in the feed mixture. So there are different types of heterogeneous azeotropic system, and in our system of IPA water and the cyclohexane, it consists of an three additional azeotropes. One is binary homogeneous azeotrope and binary heterogeneous azeotrope, and the third one is the territory heterogeneous azeotrope. So our feed state. So coming to our problem statement consists of an feed mixture of 100 kilomoles per hour of an I, IPA and water with a mole fraction of zero point 0.5 mole fraction of IPA and zero point 0.5 mole fraction of water. So let's give input IPA and water, cyclohexane. Just to save this time, copy IPA, water and cyclohexane. Here we will use the NRTL method. So the NRTL parameter that is given in the question will give their inputs IPA water and cyclohexane NRTL parameters. IPA water parameters are 0, 0, 185.4, 777.3 and 0.5. This is in the Kelvin. And IPA cyclohexane parameters are 0, 0, 294.6 and 622.5 and 0.5. And cyclohexane and water are 1629, 2328, 0.242. So these are the NRTL parameters that is given in the question. So what are the NRTL parameters for IP and water? 0, 0, 185.4, 777.3 and 0.5. IP and cyclohexane are 0, 0, 294.6, 622.5 and 0.5. Cyclohexane water are 0, 0, 1629, 2328, 0.242. Now let's run the simulation. Now before we start our question, one thing I want to explain here by showing the distillation synthesis diagram. Here in both the columns we will use 1 atmosphere pressure only. As I said earlier, see our feed composition is 0.5 mole fraction of IPA and 0.5 mole fraction of water. Since it has an azeotrope around 0.7 mole fraction of IPA, so in a single distillation column we can't get more than 0.7 mole fraction of IPA in the distillate. So that's why we are adding then cyclohexane. As I said earlier, five minutes back, whenever we want, whenever we add the cyclohexane into this feed mixture, it forms three additional azeotrope. One, cyclohexane form an heterogeneous azeotrope with water. Here you can see that the cyclohexane form an heterogeneous azeotrope, because this is heterogeneous region and this is homogeneous region. This solvent form an one additional azeotropic, which is heterogeneous with water and also homogeneous with IPA. So this is homogeneous region. As I said, this is homogeneous region. So it forms three additional azeotrope, one heterogeneous azeotrope, one homogeneous azeotrope, and third one is a tertiary mixture of an heterogeneous azeotrope. So three additional azeotrope the cyclohexane get formed. So coming to our question, and we will use this diagram to synthesize our flow sheet. So this we will use as a route map to construct our flow sheet, as our it is just a rough estimation. Suppose if our feed mixture consists of a 0.5 mole fraction of IPA and 0.5 mole fraction of water means, so this is our feed composition. Here what we can do, here you can in the first distillation column, because our water is in this distillation region and our IPA is in this distillation region and our cyclohexane is in this distillation region. So what we do in the first distillation column, we will mix as I said, this is a heterogeneous region. This is organic phase and this is aqueous phase. In the first distillation column, we will mix this feed composition and this aqueous region as an input. So in the first distillation column, we will get in the bottom we will get almost 99.9 of water at the bottom. We will get at bottom 99.9 of water, and at the top you will get this picture. Later that you will give this distillation and this organic phase as feed to the second distillation column. When we give this distillation D1, which comes from the column number 1, as a feed to the second distillation column, and additionally we can give the organic phase here in the second distillation column. You will get IPA of almost pure IPA of 0.999, 0.99. In the bottom, in the second distillation column, you will get at the bottom of 0.99 of IPA, and at the top you will get suppose, and this is an approximate one only. At the bottom you will get the pure IPA, at the top you will get this tertiary mixture. Not only tertiary mixture exactly, for example you will get the tertiary mixture means later that we can split this one into organic phase and the aqueous phase. So by this rough diagram we can construct the flow sheet. Okay, so I'm repeating it again. In the first distillation column we have the two inputs. One is feed and also this organic phase. From this feed and aqueous phase, from this feed and organic phase as input to the first distillation column, at the bottom you will get water, and at the top you will get the one distillate, and this distillate is given as feed to the second distillation column, and another input to the second distillation column is organic phase. When you give this two input to the second distillation column, at the top you will get this vapor, and at the bottom you will get the pure IPA, and this vapor will again split into the two phases, organic phase and aqueous phase. and this vapor exactly no need, and this vapor not exactly at this region only, means it, and this point will lie any other, means any other area in this region, not only at this region. So I'm just giving this approximation only. Okay, but this point will lie in this region only. Okay, so let's construct our flow sheet. From whatever information you have, we have only little information. What information we have? We have the feed flow rate of 100 kilomoles per hour with a composition of 0.5 mole fraction of IPA and 0.5 mole fraction of water. Okay, let's construct our flow sheet. We will use mixer block here. Here we will have feed, what is our feed composition. So before that I will use my own units. I don't like this unit notification. So what are my units, sir? Let's use mole per minute here. Let's use atmosphere at here. So when you set these units, means it will defaultly set the units. So heat I will use megawatt only. For my units. Okay, now coming to the, now here we will use pump here. Let's construct this one. And this is feed to the column number 1. The pressure will increase to 10 atmospheric pressure and pressure drop of 8 atmosphere. What are our feed conditions? 25 degrees centigrade, and on atmosphere we have 100 kilomoles per hour. 100 kilomoles per hour of water with a mole fraction of 0.5 and 0.5. Now we will use a rectified column here. This is our column number 1. Now what are our inputs? Let's let the number of stages be 10. After that after it get converged, later we can optimize this one. Let number of stages be 10, and the condenser be the total condenser. Let's our steady state degree of freedom is 2, so we can use any two steady state degree of freedom, either reflex ratio or revolutivity or distillate rate or revolutivity. So we can use any number of two combinations. Let use the revolutivity of 3 megawatt and the reflex ratio of 2 atmospheric pressure. Sorry, 2 reflex ratio of 2 and the revolutivity of 3 megawatt. Let's our C stage be 6 and the pressure be 1 atmosphere and the pressure drop of 0.01. Let's run the simulation. After that, now we are giving this distillation 1 as C to the column number 2. So what? So before that, just put pumps and valve so that it won't show any warning like feed pressure is less than the column pressure, like that. Let's put pump. Valve number 2. And this is feed to column number 2. Let's increase the pressure of 10 atmosphere and pressure drop of 8 atmosphere and run the simulation. Now let's continue from here. Now after this, before we give this as a feed to the second column, what we do, we will put some mixer block here. And this is a pure makeup stream of cyclohexane. So this is a makeup stream of pure cyclohexane with an temperature of 25 degrees centigrade and pressure of 1 atmosphere and mole fraction of 1. So here the condition is we have to get the feed flow rate so that the composition of these three component IPA, water and the cyclohexane has to lie in this region. Then only we will get IPA at the bottom and the vapor at the top in our second distillation column. So we have to give any random value, let's say 2 mole per minute, and run the simulation. And we have to see these mole fractions, and we have to copy these mole fractions in notepad. And the next step is we have to go to this distillation synthesis diagram. So whatever the mole fractions we get, just copy and paste. So this is the mole fraction these are the mole fractions we get after we guess one makeup stream flow rate. So that fluid flow rate is in this. So this is the mixing point we. This is the mixing point we get here. So we have our guess value is wrong. So we have to guess the value. That mixing point has to lie in this region. In this region. So we have to guess the different feed flow rate values till our mixing point has to lie in this region. So it is very hectic task just to get the approximate value. So we can use our engineering knowledge to solve this one using the lever rule. So as our distillate composition, as our distillation so this is our distillation composition. So and the second way to solve this one is, so this is our distillation composition 0.609, 0.390. So what we do, we just our distillate D1 composition is 0.609 and 0.309. These are 0.609, 0.3900. Okay. 0.09 and 0.390. So this is our distillated one composition. So for that we are adding pure cyclohexane. So we just connect these two streams, our distillation one composition and a fresh cyclohexane. These 2 points, just we will connect this. So what we do, wherever this point touch in this line, wherever this point touch, we will use the lever rule and calculate and calculate the pure cyclohexane flow rate. When I use the lever rule here, so this is my distillation composition, this is my fresh cyclohexane composition, this is my mixing composition. So by using the lever rule, the flow rate I get here is 1298.2333 and run the simulation. Now let's check whether our guess value is right or wrong. Go to the results. So these are the compositions we get. Let's copy and paste here. 0.31 of 0.31. Okay, .31. Let's check 0.31, 0.20 of water. These are the remaining. So you can see here, this is our mixing point. This mixing feed composition is lying in this region. So our guessed makeup stream is correct. Now delete this stream. Now delete this makeup block, sorry, this mixer block. And now let add the second distillation column here. Now connect these streams, D1 and makeup stream. This is D1 and this is the makeup stream. Here we have the vapor, here we have B2. So we are expecting IPA has to come here. This is vapor and this is B2. Now let's give the input to the column 2. Let the number of stages here be 18. So it's just an approximate value only. After that we will optimize it. The condenser here has to be no condenser, we are using external condenser, and we are expecting vapor split here. So we are expecting two liquid phases here, one aqueous phase and organic phase. So that's why we are using the vapor liquid. So here Aspen also suggesting you that the three phases are considered in the column calculations. Means whenever we have the two liquid phases, we can use this vapor liquid option. Now we can use the strongly non-ideal liquid. Why we are using the strongly non-ideal liquid? Because as I said here we have the three distillation boundary. So it is somewhat complex heterogeneous azeotropic distillation. So that's why we are using the strongly non-ideal liquid. So we can use either strongly non-ideal liquid or azeotropic one also. But here we have the three distillation boundaries, so that's why we are using strongly non-ideal liquid. Else we can use azeotropic also, it is not at all a problem. Now the bottom rate. So we have to, so here we have one steady state degree of freedom. Either we can use bottom rate or reflex ratio or reboiler duty. So we have to guess the bottom rate or reboiler duty. That's why it, so then the column 2 has to converge initially, then we will manipulate later. So for the initial values I use the lever rule here. From the lever rule here I got the bottom rate of 378.1321. How I get this 378.11321 is by using the lever rule calculation. I hope you are aware of this lever rule. Bottom rate. Makeup stream, here we will give in the stage number 1 on stage. This is substitute to column 2 is in the stage number 2 on stage. Pressure is 1 atmospheric pressure and the pressure drop of 0.01. And we are expecting second liquid phase has to contain water. Second liquid phase means mostly organic phase only. 1 to 18, because we don't know in which stage our splitting will get happen. So we are asking Aspen to just calculate itself which stage contain these two liquid phases. Let's run the simulation. Now it get converge. Now what I'm saying is as we have one steady state degree of freedom, so as we have one steady state degree of freedom, instead of using bottom rate we can use reboiler duty also. As I said we can use any value. Let's use bottom rate here. In the result section, go to heat duty. Here we can use the bottom rate. Now run the simulation. Now let's continue simulation. Now here as we have the vapor rate here, so we have to cool it using the external condenser. As I said earlier to you, you can use external condenser here. Here you can use 40 degrees centigrade and 1 atmosphere. Why we are using particularly 40 degrees centigrade and 1 atmosphere? The reason is very simple. When you use 40 degrees centigrade and 1 atmosphere, it means we can use a cooling water here. If you put any 25 degrees centigrade and 1 atmosphere, it means instead of cooling water, you have to use chilled water or any brine solution in industry, which is very costly compared to the cooling water. So that's why we are using 40 degrees centigrade and 1 atmosphere particularly. Later that, as I said earlier, we are expecting the phase split here. So let's use decanter here. First liquid means mostly organic phase only. Okay, organic. Second liquid means aqueous. In the diagram, as I said earlier, we are connecting feed stream and aqueous stream, and whatever the distillate we get here, this distillate one we are connecting this distillate one and organic phase, we are giving feed to the second distillation column. So we are going to connect this aqueous stream in this mixing point. So we are just implementing this line, feed stream plus aqueous stream. Okay, feed stream plus aqueous stream. Bottom we will get water, pure water, and at the top you will get the vapor. So we are just implementing this line, feed plus aqueous. Before you connect this, for this 1 atmospheric pressure and 40 degrees centigrade and water. And before you connect this one at here, we will use Newton method to convert the simulation, and also the in advanced sheet we will use stable math because as I said earlier, it is a three distillation boundary synthesis flow sheet. So we will use Newton method here. So this is somewhat complex flow sheet compared to the other heterogeneous distillation columns. So we'll use here Newton method. So go to setup, go to custom, and in convergence Newton 200, insulation method azeotropic, damping level is medium. In advanced sheet, stable math, use Douglas strategy and run the simulation. Same have to done for the column number 2. First we have to go to setup, custom, and then go to convergence. We will use a Newton method here. Number of iterations 200. Initiation azeotropic, mild, advanced steep, Douglas strategy. Let's see the simulation for safe. Now, as I said earlier, we are slowly implementing this one: feed plus aqueous, bottom water, top vapor. We will open the results here and run the simulation. Now we are doing this. We have feed plus aqueous, we have the distillation plus W1, and the second step is whatever distillation D1 we get here, we are connecting this one with the organic one. Now we are implementing this operating line: D1 plus organic, D1 plus organic. Let's connect into organic. One on stage. Now open the stream results here. And let's run the simulation and save the simulation. Now we can apply the design spec here, because why? Because we have to control the water at here. Because what happened, at the bottom, if you control the water flow rate, means in the stripping section, the remaining water in the column number 2. Okay, I will show you. Okay, I will show you the next the diagram. See here, if you control the water at here, then the water will go in the rectifying section of the column number 2. Later that it will goes into the decanter. It will that water will go into the aqua stream, and later that water will comes into the W1, so that our purity of water will get increases, quality and the quantity of water will get increases if you control the water purity in the stripping section. So I'm repeating again: if you control the water purity in the stripping section, the water will goes into the aqua stream, and and then it will and then it will collect into the stripping section of a column number 1. So the quantity and the quality of water will get increases. So that what we do, we will apply the design spec here. In column number 2, we'll apply the design spec. Mole purity. Whatever the mole purity, whatever the mole fraction of water in column number 2, you just copy that mole fraction. You just copy this mole fraction and paste it here. We want water in the bottom. In the bottom, we are manipulating the water in the column number 2. Okay. We are wearing this one with the reboiler duty. .00012, let's say 100 megawatt, and run the simulation. As we are using the Newton method here, we will slowly decrease the tolerance level. This much tight tolerance is not needed. Let's slowly lose the tolerance of the water purity. E power minus 15 to e power minus 14, let's say, and run the simulation. Slowly reduce slowly reduce the tolerance level, because we are using the Newton method. Otherwise, it will show you the error. Okay, and run the simulation. Slowly reduce the tolerance level to 0.001. Otherwise, I am saying you it will show you the error, because here we are using the Newton method. Slowly reduce the tolerance level to 0.0016. 0.002, let's say. Yeah, so I slowly lose the tolerance level of water to 0.002. Now let's go to the column number 1. What is the column number 1? What is the column number 1 situation is? In the column number 1, as our feed has 833.33 mole per minute of water. So what? So we have we got an almost al- almost 833 of water in the bottom. So quantity we have obtained, but the quality we didn't obtain. But because we get the mole purity of only 78.5% only. So the quantity is good. Whatever the mole flow of water, we have received the almost water flow rate, but the quality is not at all good. Because we have received only 78.5 mole fraction only. We want 99.99 purity. We want both the quantity and also the quality. Quantity is good, but quality is not good. So what we do, just to increase the mole purity, we will manipulate this flow rate with the reboiler duty. For that, let increase the reboiler duty here. Suppose we increase the reboiler from 3 to 3.2. Just so our mole fraction is 78.5. If I increase the reboiler duty, you can see here the mole purity is get increasing from 78.2 to 81%. So slowly increase the reboiler duty. I'm saying slowly increase the reboiler duty. Don't give 4.2 suddenly, then it will show error. As I said earlier, we are using the Newton method. Let give 3.4. Slowly increase the reboiler duty. Slowly. 85. Okay, we want 99.9. 3.6. 3.8. Okay, 92.7, but we want more purity. Let's give 4. 96.9. Let's give 4.1. Let's slowly increase the reboiler duty. 99.1. Let's do one thing, but we want 99.9 purity. Let's give the purity as 4.2. Let's increase the reboiler duty as 4.2. Yeah, so we have achieved 99.99, almost pure water. So now what we do, we apply the design spec here. Mole purity, we want 0.999 of water. We want 0.99 of water at the bottom. We will use the reboiler duty at here from 0.0012 to, let's say, 1000 megawatt. Stream results. See here we have obtained 0.99 of purity of water. So we have, what about the quantity? Let's see both quantity and quality here. So in the column number 1, as our feed has 833.33 mole per minute of water, so we have almost recovered 829 of water. So quantity is good. Then what about the quality? Quality is also good. So we have pure water at the bottom. Both quantity and quality both are good. Now let's go to column number 2. So column number 1 is okay. Now let's go to column number 2. Now what about column number 2? Let's go to the stream results in column number 2. See, in the column number 2, we want at the bottom IPA. See, as our feed has 833.33. In the bottom, the quantity almost we have recovered 832.504 of IPA. Quantity is good, but what about the quality? Quality is worst because the purity is only 38.9, because we have recovered almost 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 99.9, means almost 833 of 88 833 mole per minute of IPA at the bottom number 2, but the quality is bad. We can say simply worst because among I along with this IPA, cyclohexane also getting from the bottom. So we don't want, so we can reduce the cyclohexane. And also you can observe one more point at here. In the makeup stream, almost whatever cyclohexane we are getting at here, that is get leaking at the bottom. So what we do, we will just reduce this makeup stream slowly till the purity gets to 0.995. Okay, now let's open the makeup stream. Now let's check the IPA purity at the bottom. Suppose 0.1200. Suppose we give 1200. See, our purity of IPA get increasing when you reduce the makeup stream, but our quantity is not at all reducing, but our quality is increasing. So let's slowly increase the purity of IPA through reducing the makeup stream by 100, 1200 to 100, 1100. I'm saying slowly reduce this makeup flow rate. If you can't reduce it slowly, then obviously it will show you errors or errors. You can ignore the warning. I'm saying you can ignore the warning, but you can't ignore the error. Slowly reduce this value because we are using the Newton method here. See, 1100 to 1000. Decrease by 100, 1000 to 900. I'm saying slowly reduce this makeup stream. Don't suddenly reduce from 1200 to 900. It will show you error. I'm repeating again because otherwise you will face the error. 900 to 800. Slowly decrease the makeup stream 100. Then you can see here from 0.47 to your purity is getting increasing from 50%, 47 to 50. 800 to 700. To 600. Reduce by 100. Even though you get the warning here, don't worry about the warning. Okay, slowly reduce the value. 600 to 500. Don't worry about the warning, it will go. 600 to 400. Otherwise you can do one thing, go to convergence. In this convergence function, go to methods. Let's increase the maximum closure to 40. Okay, don't worry about the warnings, it will go. $400 to $300. See, I said now, don't worry about the warnings, it will go automatically. And save the simulation. 300 to 200. Even though you get the warning again, don't worry about the warning, just keep on reducing the makeup stream 100. Even though you get the warnings, it will go automatically. 200 to 100. %89. Okay, from 100 now just reduce from 10. 100 to 90. So our purity is also get increasing when you're reducing the makeup stream. 90 to 80. 80 to 70. Reduce, slowly reduce the value, otherwise you will get the error, not warning. 92 to, so 70 to 60. 93%, but we want 99.5 at least. 60 to 50. 50 to 40. So now it's showing warning, but don't worry about this warning, just keep on reducing this value. 40 to 30. 30 to 20. Don't worry about this warning, it will go automatically. 20 to 10. 10 to 8. So here you can observe that your warning get eliminated now. So don't worry about this warning, just keep on reducing this value, but slowly reduce the warning, otherwise it will show error instead of warning. Our purity is 0.998 and we have recovered almost 832. Let's keep reducing it. 8 to, let's say, 6. So you have recovered almost 0.990. 6 to 5. It will show warning again, but don't worry about it, keep on reducing it. 5 to, let's say, 4.5. 0.993. Okay. 3.7. You got 0.993. Let's keep on reducing it. 0.3.6 and run the simulation. So we have recovered almost 0.993, but let's reducing it because because we want 0.995. Let's keep reducing this value. 3.5 to 3.4. So we have almost recovered this 0.993. Let's keep on reducing it. Okay, we have almost recovered 0.995 here. Three point two. Okay, now what we will do, we will change the destination from here to here and run the simulation. So here you can observe here, I think we have almost reached the end of our simulation. B1. Okay. As our feed consists of 833 of IPA and 833 of water. So in the bottom number 1, we have recorded almost water of 831 with a purity of 0.999. What about IPA? We have 833 of IPA and we have recorded almost 832.509 of IPA with a purity of 0.995, almost 0.995. Now here one thing you can do here externally is you can use the transfer block. What is the use of this transfer block? Means whenever you have any makeup stream, we can use this transfer block. Uh, in the extractive distillation, we are using the calculator block. Even though we have the makeup stream, we are using the calculator block at there. So that's why we didn't use any transfer block at there. So here we didn't use any transfer block. Sorry, here we didn't use any calculator block, and also we have the makeup stream. So that's why we are using here transfer block. When transfer block has to use whenever you have the makeup stream and whenever you don't use any calculator block. So let's use the transfer block here. So we want to transfer enter cyclohexane from here in B2 to makeup stream. We want to transfer this B2 cyclohexane we want this B2 cyclohexane. We want to we want to transfer this B2 cyclohexane to the makeup stream. Mole flow. Now we are transferring from B2 cyclohexane to makeup cyclohexane. Now let's run the simulation. Okay. Now here you can check your results. W1 purity of 0.994, 0.999. At the bottom 2 we get IPA. At bottom 1 we get water. I hope your simulation got converged without errors and warnings. Thank you.